Hello, this is Nathan Little from the Room team. Today I'm joined by Daniel Clausen, who's responsible for computer vision, Claire Persinger for hardware and power delivery, Ethan Robotham for the embedded system integration and communication, then myself for the web development and robot path planning. The Roam robot is an autonomously guided three-wheel robot with a swivel in the rear. The LiDAR sensor and Pi processes the environment and determines the movement. The SIM7600 cellular module and ESP32 take the coordinates and allow for wireless data transmission, and the camera and Raspberry Pi enable object identification and classification. For the engineering specifications, our goals were to reach greater than 70% accuracy on the object classification, with an object detection range between half a meter and 3 meters from the robot. The next specification was to follow the sidewalk without drifting off course for longer than 25 feet. In addition, some important mentions. It cannot travel faster than 10 miles per hour, and the GPS accuracy and upload time should be within 20 meters and less than 2 seconds respectively.
Think of the system as 3 cooperating loops: perception, control, and telemetry. The Raspberry Pi runs the perception stack, which consists of the LiDAR and camera, then publishes a single control intent over UART as JSON to the ESP32. The ESP32 owns real-time control. It validates packets, applies deadband and saturation, and drives motor PWM safely, while a small state machine updates the LCD and buzzer for faults. In parallel, the ESP32 manages the SIM7600 G-H. It awaits for the GPS fix, timestamp data, buffers when the cellular is down, and posts longitude and latitude to a server when online. The website simply parses, stores, and serves as a live map and log view.
This is the body of Roam. So you can see it's made out of wood with 6-inch wheels. This back here is the 12-volt battery that powers the rest of our system, and then you can see we have our PCBs. This first PCB is our 3.4 volt regulator, and at the top there are 2 pinouts, one that takes the 12 volt battery in and turns it into 3.4 volts out, and it will supply about less than 1 amp, and this will be for our ESP32 as well as our SIM76 module. This next regulator is our 5.2 volt regulator, and this is for our Raspberry Pi and LiDAR. There is a 12 volt in power that will take the 12 volts from the battery and regulate it to 5.2 volts, and it won't use more than 3 amps. Lastly, we have our main MCU board. So this is to supply power to everything else, and first you can see the ESP32 front and center, and that's receiving information from our UART to USB converter. We're also going to use the motor driver pinouts on the bottom to supply logic, as well as 3.4 volts to our motor drivers. And then we have our battery voltage in that will split the power coming from our 2 batteries to where it needs to go with the regulators and the motors. And then we have what will go to our regulators from our battery, as well as the connection back into this board, which is our 3.4 volts powering the ESP32. Next, we have the motor driver, which is a dev board. This is our motor driver that we will build on a PCB, and it is to power the big motors we have. We also have our Pi and then the LiDAR spinning at the front. And here you can see the motors that will be powered by the motor driver. For overall functionality, we are going to show the robot driving in a test case scenario surrounded by pictures of furniture, and this is supposed to simulate a real-life situation of it identifying trash or treasure on the side of the road. And we will also show the GPS update to the website to show that we can lock this trash and treasure onto a certain location. Here you see it slowly driving down this track, and along the way it is taking pictures and identifying the trash and treasure, which you can see on the next slide. You can see it identifying this treasure. We have a cabinet, and then we have this couch. This takes multiple pictures as it drives down this little path, so there's multiple pictures we're able to provide.
What's shown here is how our GPS is integrated into our project. The top left is Google Maps with my live location, the right is our website, and the bottom left is the Arduino code. After we upload the code, the Sim7600 brings up the data by sending a few key AT commands. The main ones are connecting to the carrier's APN and prepping HTTPS, confirming an IP, starting the HTTP service, enabling TLS, and setting the URL and JSON content type. Now, when the Pi flags trash or treasure, the ESP32 requests a GPS fix from the modem. It wraps the longitude and latitude in JSON and posts it, which is read by the server. The website receives this and plots it on the map, as shown here.
One of our key engineering specifications is ensuring Roam can correctly detect and identify objects within a range of 0.5 meter to 3 meters, while maintaining an accuracy of at least 70%. To do this, we measured out and marked distances of 0.5 meter, 1.5 meters, and 3 meters, and tested Roam's object classification software at these three ranges. This live demo shows the specific case of the cabinet being detected at all three ranges. Each item was given about 20 seconds at each range to detect the object. Here are the results of the test you just saw. These pictures were taken and identified by Roam at all ranges. Currently, this test was only done indoors. Because of this, Roam's ability to detect smaller objects like trash was hindered, so we decided to stick with furniture items for the distance test. These are the results of all 10 trials. The cabinet is the live demo you just saw, and altogether this shows a total accuracy of 66% across all distances. 0.5 meter and 1.5 meters both had an accuracy of 80%, while at 3 meters the accuracy drops to 40%. This result is expected as Roam should be less accurate the further away the object is.
Do you want to help him by holding something for him?
No,
No, I think this is cool.
I don't think this is getting it.
It's not getting it.
So I guess what we...
Oh, put it further back. Put it near the lamppost.
Is that too far?
While testing Roam's object detection accuracy, there was a very noticeable difference between Roam's ability to detect furniture and its ability to detect trash. Roam succeeded mostly with furniture objects, and this is because of two reasons. The first being the testing environment. It isn't similar to the one Roam was trained in, and an outdoor test would likely yield more promising results for trash detection. The second being the weakness of the Roam dataset. The images of trash it was fed don't have enough variety for the kinds of trash you are likely to see, causing Roam to effectively only detect white pieces of trash when they're unobscured. This table shows each of our trials trying to get Roam to detect different objects while running or stationary, and shows its lack in ability to detect trash but was reliably detecting furniture.
For our testing of the autonomous driving, we ran 3 tests here. 2 will show a failure, and 1 will show a success. We need to tune the path planning and object avoidance before bringing it to the outdoor environment on the real sidewalk. The motor's duty cycle and distance from objects need to be further tuned and calibrated in the coming weeks in order to match the LiDAR logic running on the Raspberry Pi, in order to deploy a fully functional robot. In the table, we go through the runs that had and didn't have collisions, and how far each of them traveled.
What is left? There are a few things left to improve to make our project the best that it can be for demo day. The first being LiDAR testing to improve accuracy. Obviously, there were a few times that our LiDAR got off track, so we would like to improve that, making sure it doesn't bump into anything and it stays on pace. The next is the motor driver and PCB testing. For this, we want to fabricate and make sure our motor drivers work exactly as expected. Next, we have to improve the database for object detection. This means that we're going to provide the model with more photos so that we can more accurately detect specifically trash. Next, we have to improve the chassis build. The wood we have is pretty heavy, meaning that there's a lot of strain on our motors. So we'd like to improve the design so it can be more efficient and put less strain on the motors. And then the last thing we have is to integrate the Pi in our battery power source, because we didn't want anything happening to the Pi as it was very difficult to put together in the first place. So during testing, we had it connected to a separate power source, which we will connect to our overall power source